Hello children, welcome to Physics Learning Point. Today our topic is quantum mechanical model of an atom. According to Niels Bohr, the electrons revolve around the nucleus in particular paths or orbits. If electrons revolve in well-defined paths, the position of electron at particular time or at instant time will be known. Then, what is the velocity of electron and position of the electron? Electron is a small particle which is invisible. Then how can we recognize its velocity and its position? Generally, in a dark room, if you want any object, there is no power, there is no light, then what we do? Just we bring a torchlight and we focus the object with torchlight. Similarly, here the electron is invisible. It's very small. The size of the electron is very small. To know its properties, just like position and its velocity, we need to use a light which has the wavelength equal to the size of the electron. If we use that type of light which has the wavelength equal to the size of the electron, then this light, whenever intersects the electron or interacts with the electrons, then electron changes its path and direction. Then we don't get exact the velocity and the position of the electron. So from this, some questions arises. Electron revolve in a particular orbits. Yes, exactly. The electrons not revolving around the nucleus in a particular orbits. Based on these observations, new atomic model was introduced. That is nothing but quantum mechanical model of atom. And this quantum mechanical model was developed by the scientist Erwin Schrödinger. According to quantum mechanical model, the electron is not revolving around nucleus in a particular orbit. The electron is revolving in particular region of space around the nucleus, and this region is named as orbital. And these orbitals have different energies as per their position. To explain the position of electron and the velocity of electron, instead of orbits of Bohr's theory, the electron is revolving around the region around the nucleus in a region of space that is called orbital. The probability of finding electron around the nucleus is called orbital, and different orbitals have different energies. The orbitals which are close to nucleus, they have lower energy. The orbitals which are away from the nucleus, they have higher energy. Each electron in the quantum mechanical model is described by set of quantum numbers. Initially, 3 quantum numbers are there. These are principal quantum number, angular momentum quantum number, and magnetic quantum number. Later, one more quantum number is introduced, that is spin quantum number. So, these 4 quantum numbers explains about the electron position and energy and everything about the atom. So come to the principal quantum number. Principal quantum number generally denoted with the letter n, and the principal quantum number is related to the size of the atom and energy of the atom. And the principal quantum number has the values n equal to 1, 2, 3, 4, so on. These are the values. The principal quantum number is n and having the values 1, 2, 3, 4, so on. If n equal to 1, then this is the first orbit or k, represented with k, and if n equal to 2, this is the second orbit and represented with L. If n equal to 3, then this is third orbit and represented with M and N, so on. The values for principal quantum number are 1, 2, 3, 4, and these orbits represented with K, L, M, N. Then, how this principal quantum number explains the size and energy of the atom? If principal quantum number increases, then its energy increases. For example, if n equal to 1, then that atom has only one orbit. So its energy is only orbit, one orbit, it has very less energy. That atom has less energy. Then if n equal to 2, that atom has two orbits. So the orbits which are close to nucleus have less energy. The orbits away from the nucleus have higher energy. As the number of the value of n increases, for example n equal to 4, then it has 4 orbits around the in that atom, it has 4 orbits. So its atomic size is increasing, as well as the orbit, as the orbits increases, its energy also increases. In this way, the principal quantum number explains the size of the atom and energy of the atom. As the n value increases, the size increases and its energy also increases. And next, come to angular momentum quantum number. The angular momentum quantum number, also known as azimuthal quantum number, and it is denoted with L. And angular momentum quantum number, also known as azimuthal quantum number. And this angular momentum quantum number mainly depends on principal quantum number, and the values of L or angular momentum quantum number depends on principal quantum number. And the L values are: the minimum angular momentum number is 0 and the maximum number is n minus 1. For any given n value, the minimum L value is 0 and maximum L value is n minus 1. So it is depending on principal quantum number. For example, if n equal to 3, then how many number of L values are there? The equal to n value, 3 L values are there, because the n equal to 3 and L values, total L values are 3 depending on principal quantum number. So minimum value should be, the L value minimum value should be 0 and the maximum value should be n minus 1. So 3 minus 1, 2. So this is about that values of angular momentum quantum number. So here the principal quantum number is 3. So how many L values are there? 3 values. And what are those values? The minimum value 0 and the maximum value should be n minus 1. So 0, 1, 2. Similarly, if the n value is 4, principal quantum number is 4, then how many L values are there? Total 4 values are there. And these L values are, so minimum 0, then maximum is n minus 1. So 4 minus 1, 3. So total 4 values are there. And these L values, if L equal to 0, that is S orbital or S subshell. If L equal to 1, and that is P, and if L equal to 3, if L equal to 2, that is D, if L equal to 3, that is F. So here the angular momentum quantum number mainly explains the subshells present in the main shell. So for example, in third main orbit, how many subshells are there? 1, 2, 3. So 3 subshells. If L equal to 0, that subshell. If L equal to 1, that subshell is P. If L equal to 2, that subshell is D. If the angular momentum quantum number is 3, the subshell is F. So according to Sommerfeld, we know that the main shells again splits into subshells. Then how many subshells are present in the main orbit, main shell, is explained by the angular momentum quantum number. Based on, depending on principal quantum number, the equal number of subshell will be there. If third orbit, how many subshells will be there? 3 subshells. What are those? It represented with angular momentum quantum number. So minimum number 0, the maximum number n minus 1. So 2. So 3 subshells are there. The values are 0, 1, 2. Then if subshell S, its L value is 0. If subshell P, then its L value is 1. If subshell D, its L value is the 2. So in this way, the angular momentum mainly explains about subshells and its shapes of the subshell. For example, that S orbital has the spherical in shape, and P orbital, it is in dumbbell shape, and D orbital in double dumbbell shape. Subshells and their shapes are explained by the angular momentum quantum number. Then again, if subshell belongs to the first orbit, so first orbit, the principal quantum number is n, and its L value, only L1 L value is possible. So that is 0, because the L values are 0 minimum and maximum is n minus 1. So 1 minus 1 also 0. So only one value is present, that is S orbital. Then the subshell of first orbit is denoted with 1s. So 1s, and this one represent the principal quantum number. Okay. Similarly, then second main shell divides into 2 subshells. So here n equal to 2. Then how many subshells are there, or L values are there? 0. Minimum value 0, maximum is n minus 1. 2 minus 1, 1. So 2 subshells are there. These are S, and if L equal to 1, that is P. So these subshells belongs to second orbit, so represented as 2s and 2p. Similarly, the subshell belongs to third orbit. If n equal to 3, then L values are, subshells are 0, 1, 2, 0, s orbital, so 3s, 3p, 3d. Similarly, if n equal to 4, then how many subshells? 4 subshells, S, P, D, F. So then these subshells are represented as 4s, 4p, 4d, 4f. In this way, the angular momentum quantum number mainly explains about the subshell and their shapes. S orbital in spherical in shape, and P orbital dumbbell shape, and D orbital double dumbbell shape. Now come to the magnetic quantum number. So these subshells again divides into number of finer shells. So the orientation of these subshells in the space or region of space explained by the magnetic quantum number. This magnetic quantum number is denoted with ml. So this magnetic quantum number mainly depends on angular momentum quantum number. For any L value, total M value and magnetic quantum numbers are 2L plus 1. So, magnetic quantum number mainly depends on angular momentum quantum number. So, for any given angular momentum quantum number, the total number of ML values or magnetic quantum number values are 2L plus 1. The minimum value is minus L and the maximum value is plus L. So, for example, if L equal to 1, this L equal to 1, that is nothing but p orbital, p subshell. So then this p orbital again divides into 3 finer subshells. So how it divides? So L here 2L plus 1. So 2 into L value is 1. So 1 plus 1. Then how many L values are there? 2 into 1, 2 plus 1, 3. Total 3 magnetic quantum numbers are there for this L value, which means the p orbital again divides into 3 finer subshells, orbitals. So their values are, the minimum ML value is minus L. So here L equal to 1, that is minus 1, 0. The maximum value is plus L. So plus 1. So the p orbital again divides into 3 finer subshells. So and these p orbitals are denoted with px, py and pz. Then how these orbitals oriented in the space is explained by the magnetic quantum number. These 3 orbitals have same energy. This type of orbitals are said to be degenerate orbitals, and the d orbital dividing into 5 subshells. So suborbitals dxy, dyz, dzx, dx square y square, dz square, and these 5 d orbitals have same energy. This type of orbitals are said to be degenerate orbitals. The orientation of p orbital generally like this. So the px always along with, so dumbbell shape p orbital, and this is the px orbital and it is x axis, and the py orbital, it is along with y axis, this is py, and let us say this is a z axis, and one more p orbital is oriented along z axis, then that is pz. This orientation of the orbitals is explained by the magnetic quantum number, and the magnetic quantum number explaining the subshells and orientation of the subshells. So next come to spin quantum number. Up to now we come to know that the energy of atom and about the shells and subshells, and spin quantum number mainly explains about the orientation of electrons in the orbitals. So each orbital can hold 2 electrons. One electron is clockwise and the second electron is anti-clockwise. So the p orbital dividing into 3 subshells, and each subshell can hold 2 electrons. That electron, one is clockwise and the second one is anti-clockwise. So each orbital can be filled with 2 electrons, that the one is clockwise and the second electron is anti-clockwise. This clockwise and anti-clockwise orientation is explained by the spin quantum number, and the spin values are assigned to these 2 electrons. The first one has the plus of spin and the second electron has the minus half. This is about the quantum mechanical model of atom and quantum numbers. Thank you.